Hello. 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 In this presentation, I want to give a rather detailed analysis of one of the astronomical results given by Bhaskara I in his Laghubhaskariya. So this is going to be a rather detailed presentation, and some prerequisite knowledge of the celestial sphere is would help you to understand the presentation. So if you don't know what the celestial sphere is, you can have a look at the video I have created on this topic, and the link is given in the description. You would also need to know something about spherical triangles and spherical astronomy, spherical trigonometry, but I will cover those, the necessary information. I will give the necessary information in this talk. So, who was Bhaskara I? Well, he was a famous Hindu astronomer and mathematician living in the 7th century, and his works were extremely influential in the development of mathematics and astronomy, not just in India, but in the whole world. Um, he was contemporary to another famous Hindu mathematician, Brahmagupta, and some of the important works of Bhaskara I were the Laghubhaskariya, Mahabhaskariya, and his commentary on Aryabhata's works. So in this presentation, I will start with the basics of spherical triangles. So what are spherical triangles? Then I will present a important result of spherical triangles known as the cosine formula for spherical triangles. I will apply this cosine formula to the celestial sphere and derive a result which is exactly the one given by Bhaskara I, which relates the declination of the sun to the longitude of the sun on the celestial sphere. I will also give a detailed analysis of the Sanskrit text of Bhaskara I, along with its translation and explanation into English. So what are spherical triangles? To begin with, you take a three-dimensional coordinate system, x, y, z, as I've shown here, with x axis here, the y as the vertical axis and the z as this axis. And the origin, let us call that as the point O. With the point O as the center, make a sphere and take 3 points on the surface of the sphere, A, B, and C. Now, let's consider all the points pairwise. So first, let's consider the pair AB. So with the pair AB and the point O, we can define a plane which goes through these 3 points. So let's make the plane which goes through A, B, and O, and this plane intersects the sphere in a circle. And this is the circle of intersection. And now let's consider the arc on this circle which joins A and B, which is this A and B. Do the same thing for BC, and you get the arc BC. And do the same thing for the points C and A, and you get this arc CA. And this is an example of a spherical triangle here. So just like triangles in the plane, spherical triangles also have sides and angles. So this would be one side of the spherical triangle, this would be the other side, this would be the third side, and then this angle would be one of the angles, this would be the second angle here, and the third angle. So, but there are certain differences compared to planar triangles. So let's look at those differences. To begin with, the sides of a spherical triangle are not given in terms of the length of these arcs. Instead, they are given by the angles these arcs subtend at the center of the sphere. So this is not a very major difference, because the length of this arc is proportional to the angle subtended at the center. So it's just radius times the times the angle is equal to the length of the arc. So, and then you have these. So these 3 sides are defined in terms of the angles they subtend at the center, and these 3 angles. So these 3 angles, this angle A is obtained by first making the tangent at the point A to the arc AC, and the tangent at the point A to the arc AB. And then the angle between these 2 arrows will give you the angle capital A. And similarly for the angle capital B and the angle capital C. And in this case, you can see that the angle between these 2 arrows is the same as the angle between these 2 planes, AOC and AOB. To help understand this better, I have made a 3D graphic. So it's the same picture as the one which we just saw, but here you can rotate the graphic like this. And if you just bring this point A so that it is coincident with the origin, you can see that these two arrows, which are tangential to the respective arcs, they are the angle between these two arrows is the same as the angle between these planes, AOC and AOB. Okay. So carrying further, so now there is a the basic result of spherical trigonometry known as the cosine formula for spherical triangles, which is I'm going to just present that I have presented that here in this formula. So it states that the cosine of the side A, small a, remember that the side is actually the angle, this one. So the cosine of this angle A, small a, is equal to the cosine of small b times cosine of small c plus sine of small b sine of small c times cosine of this angle capital A. This is one of the most principal formula of spherical trigonometry. And I'm not going to give the proof here, but if you're interested, you can look up the proof, for example, in this textbook by W.M. Smart, textbook on spherical astronomy. And I've given the snapshots of the relevant pages here. So the proof starts from here and ends here. So it's a pretty simple proof. So it is not very difficult to understand this, but I'm not going to discuss this in detail right now. Okay, so all right. So now we're going to apply this cosine formula to the celestial sphere. So what is the celestial sphere? It's a sphere of arbitrary radius with the Earth at the center of the sphere. So this blue sphere is the Earth, blue point is the Earth, and this is the celestial sphere here. Now, there are certain concepts associated with the celestial sphere. So, for example, this is the celestial pole, P. What is the celestial pole? You you join the center of the Earth to the North Pole of the Earth and extend this line so that it intersects the celestial sphere at the point P. And the point P is the celestial pole. This is the North Celestial Pole. You will, of course, have a South Celestial Pole by going the other direction. And you know that the Earth rotates about its axis. So the axis in this case will be the line OP. So because of the Earth's rotation, all the objects on the celestial sphere will appear to rotate from east to west, because the Earth rotates from west to east. So all the objects appear to rotate like this. In particular circles, and each of these circles is called a diurnal circle. So here I have taken an arbitrary object x, which can be a star or a sun, planet, or anything. X is here. So x will be appearing to rotate along this circle. So this circle is the diurnal circle of x. Now, of course, P will not rotate because P is it lies on the axis of rotation, so it will remain stationary. Now, there are other concepts such as the celestial equator. So the celestial equator is a circle which is parallel to the equator of the Earth. And this is one of the great circles. And the ecliptic circle, the plane of the ecliptic is the plane in which the Earth revolves around the sun. So the sun will, of course, always be lying somewhere on the ecliptic circle here. Now, there is also a great circle of the sphere. Remember that a great circle is any a circle on the surface of the sphere such that its plane contains the center of the sphere. Now, and then this is the point gamma, which is the intersection of the ecliptic circle and the celestial equator. So this is also known as the point of equinox. So all these concepts I have explained in my earlier video on the celestial sphere. Feel free to check it out. Because of the Earth's rotation on its axis, the ecliptic plane also appears to rotate about the axis OP. And when you make a line perpendicular to the plane of the ecliptic, and let's say that it intersects the sphere at a point K. So this point K is known as the ecliptic pole. So the point K also appears to rotate in a circle, tracing out a cone. So, so this point K is known as the ecliptic pole. Gamma is the point of equinox, etc. So I've just made a video here so that you can have a look at this, what it looks like. So the Earth rotates, but but because of the Earth's rotation, everything else appears to rotate from east to west. So gamma is the point of equinox. This rotates along this circle of the celestial equator. Then this here is the constellation Orion. Then this K is the ecliptic pole, which rotates along this circle. This X is the arbitrary object rotating about its diurnal circle. Okay, so this would be as much as regarding the celestial sphere. Now, let us now consider the points P, K, and X. P is the celestial pole, K is the ecliptic pole, and X is the arbitrary object, the object of interest for us. Oh, now let's consider the spherical triangle PKX. So we want to apply the cosine formula to the triangle PKX. For that, we need to know what the sides of these triangles are, of this triangle are. So let us see. Let us first of all extend the arc PK so that it intersects the celestial equator at the point Q. So and let's extend KX so that it intersects the ecliptic circle at the point L. Now, now remember that OK, this is the center of the sphere is O. So OK is perpendicular to the ecliptic plane. So it's easy to see that the angle KOL is 90 degrees. And similarly, OP is perpendicular to the plane of the equator, celestial equator. So POQ is going to be 90 degrees. So, right. There are certain other things which I wanted to talk about. The angular distance of X from the ecliptic circle is known as beta, and the angular distance of L from gamma is known as lambda. So beta is known as the latitude, which is not to be confused with the terrestrial latitude, and L gamma is known as the angle lambda, which is not to be confused with the terrestrial longitude of the Earth. Okay. So these two are beta and lambda. They form part of the so-called ecliptic system of coordinates. Similarly, when you measure the angular distance of the object from the celestial equator, you get this angle delta. So this delta is called the declination. And similarly, you have the other corresponding object, which is the right ascension, which is the angular distance of Q from gamma. So QO gamma will be the right ascension alpha. So here alpha and delta, they form they are part of the so-called equatorial system of coordinates. So as I had just mentioned, KOL is 90 degrees. So this angle KOX plus XOL is 90 degrees. So let me just go here. Let's go to the next slide. It will become easier. So here I've shown it, much more explicitly. So the spherical triangle PKX is here. Let us call the side PX as small a, and PK as small b, and KX as small c. So now angle A, small a plus delta is 90 degrees because POQ is 90. So therefore A is 90 minus delta. This is here. And similarly, C plus beta is 90. So C is 90 minus beta. So we know this side of the spherical triangle is 90 minus delta. This is 90 minus beta. And now what is B, the angle B? Well, just remember that OP is the axis of rotation of the Earth, and OK is perpendicular to the ecliptic plane. So the Earth's axis of rotation is tilted to the perpendicular to the ecliptic plane by an angle of about 23.5 degrees, which is known as the obliquity of the ecliptic. So this B is about 23.5 degrees, which we will call in our notation as epsilon. So the exact value is approximate is we won't discuss the exact value, but it's approximately 23.5 degrees, but we will call it as epsilon. Okay, so we know what A is, what B is, what C is. In order to apply the cosine rule, which is cos A equal to cos B cos C plus sin B sin C cos A, we need to know what this capital A is. So this capital A is essentially this angle, capital K, here, PKX, so to speak. Basically, the angle between this arrow and this arrow. So now, what is the angle between this arrow and this arrow? Well, let's have a look. So first of all, the angle between this arrow and this arrow is nothing but lambda, longitude, this one longitude, because you can just check, verify for yourself that is the same as the angle LO gamma. Okay, so this angle is lambda. Okay, and so this angle is also lambda. Now you will be able to convince yourself, if you give it some thought, that this angle, the angle between this arrow and this arrow is 90 degrees. So you have here angle K, which in our notation is angle A, in fact. So angle K plus lambda is 90 degrees. So angle K is equal to 90 minus lambda, which is what I've shown here. So in case you are not convinced why it is 90 degrees, I've made a here a 3D graphic for that. So let's just have a look at this graphic. So as I mentioned, this angle is 90 degrees. Let's just bring this point. It is coincident with the Earth here, and there you can see that this angle is, at least visually, you can make out that it is 90 degrees. And why it is 90 degrees? It's quite easy to understand, because this OP is perpendicular to the equatorial plane, and OK is perpendicular to the ecliptic plane. And it's like, you just tilt the ecliptic plane with respect to the equatorial plane about gamma O, and then this will move. I mean, so OP and OK will be moving in such a way that this angle is actually always equal to 90 degrees. So yeah. Anyway, so the point is, this angle is 90 degrees, and this angle is lambda. So the angle capital K or capital A is 90 minus lambda. So which is what is stated here. So when you apply now the cosine formula, A is equal to 90 minus delta. So cosine A becomes sine delta. Cosine B is equal to epsilon. So cosine B remains cosine epsilon. Epsilon is the obliquity of the ecliptic. Cosine C becomes sine beta, because C is 90 minus beta. So cosine 90 minus beta is sine beta. And then similarly, sine of beta becomes sine of epsilon, because B is equal to epsilon. Sine C becomes cosine beta, because sine of 90 minus beta is cosine beta. And cos A, or cos K if you want, is cos of 90 minus lambda, so which becomes sine lambda. So this is the application of the cosine formula on the celestial sphere, which gives us this formula. And well, you can also check out on other sources on the internet which deal with astronomy. So one example I've given here is from Fiona Vincent's website from the University of St. Andrews. So the same formula you can see is given on this website here. Okay, so I'm just repeating that the same formula here, which is given here. It's the same formula here. And now suppose X is the sun. So when X is the sun, we know that the sun lies always on the ecliptic circle. So for the sun, beta will be 0, because it's always on the ecliptic circle. So when beta is 0, you have sine beta becoming 0. So this term drops off, and cosine beta becomes 1. So only this term remains. So you have sine epsilon, sine lambda on the right hand side. Left hand side is sine delta. So for the sun, sine delta is equal to sine epsilon, sine lambda. So this relates the declination of the sun to the longitude of the sun, this formula. And this is exactly the formula which was given by Bhaskara I in the Laghubhaskariya, in this Sanskrit verse here. Laghubhaskariya chapter 2 verse 16. So in the Sanskrit, this is what it reads like: Saptarandhragni rupani paramapakramo gunaha tatsfutarka bhujabhyasas trijyayeshtapamo hritah. Let's understand this verse in detail. First of all, let us look at this word Saptadandragni Rupani. So this is a way of notating numbers in Hindu astronomy and mathematics, which is the so-called Bhuta Sankhya system of notation. So Saptadandragni Rupani. So in the Bhuta Sankhya system of notation, each number has can be represented by a certain number of by certain words. For example, one can be represented by the word Surya, which means sun, because there is one sun, or moon, Shashi, moon, which is because there is one moon, for example. The number two can be denoted, for example, by netra, which means eyes. So everyone has two eyes. Then the number three, for example, can be notated by the word gunas, because there are three gunas in Hindu philosophy: sattva, rajas, and tamas. So guna, for example, would be three. You can also have agni. There are three types of fires in this. The word four, for example, can be yuga. For example, yuga means in Hindu cosmology, you have the Satya Yuga, Treta Yuga, Dwapar Yuga, and the Kali Yuga. So the four yugas, or you can have the Veda. The word Veda also denotes four, because there are four Vedas: Rig Veda, Yajur Veda, Sama Veda, and Atharva Veda. Um, okay, so in this case, Sapta Randhragni Rupani, the word Sapta is 7. That is just a literal word for Sapta. Then Randhra is 9 in the Bhuta Sankhya system of notation. Agni is one of the words used for representing 3, and Rupa is one of the words used for representing 1. So Sapta Randhragni Rupani would give you this number 7931. And in the Bhuta Sankhya system of notation, the numbers are given in reverse. So you have to reverse them. So you get actually 1397. So the verse states that this is the radius times sine of some angle. So let's see what this angle is. For that, we need to know one fact, that in Hindu astronomy, the radius of a circle is taken as 3438 conventionally, as an approximation. And the reason for that is that the circumference is taken as 21,600 units, which is equal to 360 degrees, which is equal to 360 times 60. So so one full rotation has 360 degrees, and each degree is further divided into 60 units. So a circumference is taken as 21,600 units. So when you take the circumference by diameter ratio, 21,600 divided by twice 3438, you get the value which is approximately pi. So 3.14136. I mean, this is of course an approximation, but as an approximation, this is what is taken usually in Hindu astronomy. And when you do that, you get when you substitute the value of the radius, which is 3438, and divide this 1397 by the radius, you get the sine of that particular angle, which is given by now 0.40634. And when you take the inverse sine, you get sine inverse 0.40634, which is approximately equal to 23.97 degrees. And this is the value for the obliquity of the ecliptic, which was taken in Hindu astronomy. So this is Sapta Randhragni Rupani is the R sine of the obliquity of the ecliptic. So by the way, if you want to know more about the Bhuta Sankhya system of notation, you can see the and Singh. I have actually given some snapshots from the and Singh, where, for example, the word, the letter 0 is expressed by these words. So I have given a list of, so they have given a list of words for denoting each of the numbers 0, 1, 2, 3, 4, 5, 6, 7. Yeah. Okay, so now with this information for Sapta Randhragni Rupani, let us look at the rest of the verse here. So Gunaha is the R sign. In this case, Gunaha means R sign. Paramapakramaha means the obliquity of the ecliptic, or the greatest declination of the sun, which is the same as the obliquity of the ecliptic. So 1397 is the R sign of the obliquity of the ecliptic. That Abhyasa is one of the words for multiplication. So that multiplied with the Sphutarka Bhuja. Sphutarka Bhuja is R sine of the longitude of the sun. That multiplied with the R sine of the longitude of the sun. Hritaha is divided by the radius. Hritaha is divided by what? By Trijya. Trijya divided by the radius. Trijya is by the radius. So this is the Ishta, desired Apama. Apama is the R sign of the Earth, sun's declination. So this is, you can easily verify it's the same as this formula, because in Hindu astronomy they spoke about R signs. So you have actually R sine delta is equal to R sine epsilon times R sine lambda divided by R. So if you just multiply both sides of this equation by R and R, you will get exactly what is stated here. And Trigya is known as the radius in Hindu astronomy, and it has a very interesting origin. The word Trigya. Why does it mean the radius? Well, Jya is the Sanskrit word for sine, S-I-N-E, the sinus function of modern trigonometry. So, and 3, actually they used to take as r sine, not sine, but the radius times the sine. So Jya means the radius times the modern sine, and 3 means 3. 3 what? 3 zodiacal signs, 3 zodiacal constellations. So you know, in the ecliptic there are 12 zodiac signs, and sign means SIGN. There are 12 zodiac signs, so 360 degrees has 12 zodiacs. That means that 90 degrees has 3 zodiacs. So our sign of 3 zodiacs would be in our sign of 90 degrees, which is simply r, which is the radius. So Trigya is the word for the radius in Hindu astronomy. So, and this is exactly what is the formula given here in this verse. So yeah, so here is the English translation of that from K.K. Shukla's translation of the Laghubhaskariya. Okay, and just for information, the same formula is also given in the Bhaskara in chapter 3, verses 6 and 7, just for the information. And yeah, that brings me to the end of this talk. And here are some references which you can follow up. So Kripashankar Shukla's translation of the Laghubhaskariya and the Bhaskariya are the versions which I have used in this presentation. The Bhuta Sankhya system of notation, as I have already mentioned, is discussed in detail in Datta and Singh in this book. And then and this book by Ramasubramanian and Sri Ram, this is an English translation of the Tantra Sangraha of Nilakantha Somayaji. So this is one of the this book contains a lot of important and interesting information on Hindu astronomy, astronomical conventions, on modern astronomical notations, and detailed analysis of the mathematical methods used by the Hindu astronomers up till the time of the Kerala mathematicians. So this is a translation of Nilakantha Somayaji's Tantra Sangraha. Nilakantha Somayaji was a mathematician from Kerala, one of the pioneers of calculus, along with Madhava of Sangama Grama. So, yeah, so that would be it as far as this talk is concerned. Thanks for listening in, and see you next time. Bye bye.